Okay, thank you all for coming. This is my talk on the CloudStack virtual router, the present, past and future of virtual router. So who am I? I'm a software architect at ShapeBlue. I work from Gurugram, India. I've been working with the Apache CloudStack community since last 6+ years now. I'm a committer in PMC now. I've been the release manager for several of the minor releases and most notably the recent 4.11.0 major release. I was asked, to put some stuff about what do I specialize in. That's very a tough question. So I put in some, high-level things that I think I've been working on for the last 6 years. I'm also the author of CloudMonkey, the CLI for CloudStack, and several features in CloudStack. I'm a vegetarian, I love animals, and I love programming. So that's what I do in my free time. I can see a lot of sleepyheads here, having your lunch, and but I'll try to keep it very brief and to the point. It actually helps me to know the audience. So if I may, can I have a quick show of hands, like people who come from the development-related background or who are developers? Nice, thank you. People who are non-dev, but in, let's say, sysadmin support-related stuff they're doing, okay. And I guess the rest of you would be the business managers and all the non-dev types, okay. So I'll keep it very simple and to the point, and try to be not very technical. I'll try not to go into the code now. So the topics for today's talk we'll first look at what system VMs are, what virtual routers are. We'll do a comparative study. So in order to understand the virtual router, we might want to know what's the past of virtual router, what the virtual router kind of looked like in the past. And we have some parameters to measure that. And then in order to work towards the future of the virtual routers, we need to understand what is the present like. So once we know the present, then we can maybe aim and look around and learn from others and see what the future of the virtual router can look like. And of course, as you can tell, there'll be a lot of GIFs. So if my talk is kind of boring, you can always enjoy the GIFs. All right, so what is a virtual router? So before we answer that, we have to ask the question, what is a system VM template? So in CloudStack, there are a lot of activities or operations that we want to do that cannot be simply done by the management server or the core, the orchestration plane itself. So for that, what we have done is we have created a virtual machine disk image called the system VM template. And that system VM template can become one of the several service virtual machines, like a console proxy, a secondary storage virtual machine, some sort of virtual router. It could be a simple virtual router, a VPC virtual router, and things like that. And so what a virtual router is it's basically a service virtual machine. It is something to help CloudStack orchestrate something for the users. Specifically, it implements the networking solution for your end users. So that's what the virtual router does. And the virtual router also supports all the legacy and the new and the old. All those kind of network topologies are also supported by virtual routers. Maybe it doesn't make sense, I don't know. I think I tried to give you my understanding of what virtual router actually does. In order to compare the past, present, and future of virtual router, we need to basically define what do we mean by past, present, and future. I think we can all agree all the earlier versions of CloudStack from I think 4.x, 4.0 till 4.5. I'm calling that ancient because a lot of people are not using that. 4.5 is a special case. I know there are people, they may be still using 4.5, and there is a reason that maybe we will discuss on the way. The past virtual router, what I'm calling is the version of CloudStack and the virtual routers created by CloudStack 4.6 to 4.10. The present one is the latest LTS release, the 4.11. And by future, I mean maybe the next version of CloudStack, maybe 4.12 and 4.13. The reason I'm saying 4.12/4.13 is there's a high chance that the virtual router in 4.11 still keeps, still gets to be used in 4.12 or the other, next few releases. So here's a comparative study of the virtual router, in terms of facts. So the past virtual router, that means CloudStack 4.6 to 4.9 version versus CloudStack 4.11. So the first thing we see is I've tried to do sort of diff kind of table here. All the things you see in red are kind of gone, and all the green are kind of the replacements. So the past VR used Debian 7 VZ. Initially, we used to have two sets of templates for 32-bit and 64-bit support, and eventually at a few years ago, we decided to drop the 32-bit and we moved to 64-bit. The current virtual router is based on the latest Debian 9 release. It's a 64-bit template as well. One thing you could notice is in the present virtual router, we have reduced the size by almost a gigabyte in size. And by reducing the size of the template, it kind of speeds up the orchestration of a virtual router.
Right.
The next thing we clearly see is the change in Linux kernel itself and the process orchestration tool that we use. So the past VR was based on Linux 3.2 and uses initd, and the latest one uses 4.9 with systemd. So we are all systemd enabled now. The past VR router, the source code that was used to program a virtual router was mostly in Python. It's still the same more or less in the present VR, but we did some sort of refactoring to remove some bugs, make few optimizations to make it fast and whatnot. And the other changes you see, they are all infrastructural changes. So we moved from Java 1.7 to 1.8. We moved from OpenSWAN to StrongSWAN. We updated several packages. For example, Keep Alive D is just one example. And one of the miscellaneous things, also a primary driver of this change, was Debian 7 based template. Debian 7 itself reached end of life, so we had to upgrade the base operating system anyway. We think the present VR is more secure and stable, definitely because the packages that are installed in the new template are latest ones, have the latest kernel related fixes that we saw recently. And I wanted to just thank everyone in the community with the pull request that is on the end of this slide. This was a major effort. It started in August of 2017 and lasted till December of 2017. And this was, I think I helped to put together a lot of changes from a lot of people. So for example, Will Stevens from cloud.ca, he fixed the VPN part. So we moved from OpenSWAN to StrongSWAN. Vido from PC Extreme helped me to fix the systemd scripts. And then there was Rafael, René Moser, and countless people that I don't remember now. You can move to the pull request to see. But they helped to basically report bugs, contribute some changes, and I would basically test them together. And with this pull request, what we also tried to do was reach almost 100% smoke test compliance. That means we tried to make sure that the smoke test will pass almost 100% on VMware, KVM, and Xen server. The next thing is the change in building. So the past virtual router used VirtualBox. So a lot of people had a lot of fun to set up VirtualBox on a Linux environment and do it themselves. The new virtual router is far more easier to build. Like you can build on your laptop. So a lot of people they use Packer for building Packer for building guest images, and systemvm template is just another guest VM. So you can use Packer to build the base image, and we are using the same sort of export tools and archiving tool like we did before. And we believe the present way of building is far more easy. It is consistent, so you can build on your laptop or put in a CI/CD job, use Jenkins to automate that. The next thing is, how does a virtual router patch? And we'll come to what patching means, but just for comparison's sake, I'll say the patching process uses the same fundamental idea like the past VR as in the present VR. The other thing we did was we refactored the code that does patching. So there was one single file. Many of us in the community would know that this file was the infamous cloud early config. It's a big bash script, maybe 2,000-3,000 lines of code, and it will do the patching for you. And the thing was, anytime you would make a single change, you'll have to rebuild your entire systemvm template. This was not pretty at all. So we refactored, we basically minimized the cloud early config as much as possible and put all the changes in separate directories. So now if you want to make any changes, you make a change, you create a systemvm.iso file, and that could be used to patch a system vm template. And we'll know, we'll look at how that kind of improves things. The other thing and kind of interesting thing I found was, when you are moving from an older system to a newer system, whether you are refactoring or rewriting a feature, you come across a lot of technical debt. So I've come across a lot of technical debt that has had piled up in the past VR. So for example, for no reason, the past VR would patch and reboot 1 to 3 times, depending on a specific case or a hypervisor. The new VR, the first thing I did was to refactor the scripts, make it systemd enabled, and see if we can patch without rebooting, because it didn't make sense to me. Maybe the reason why they had reboots was, just do the patching and reboot. So you don't have to take care of any missed edge case and things like that. So what we have done is, there are 0 reboots except for a specific case in VMware where the router cannot ping the control or the management gateway. Otherwise, we don't do a reboot. The other thing we have done is patching is much more faster, predictable, and you can observe. You can use systemd to basically plot a flame graph to basically see which process is taking how much amount of time, and we'll come to that in a little while. And that actually helped to optimize the patching process and boot process as well. The last thing is a serial TTY console. So you can, if you've known something like XE tools or Versh, you can use those to basically attach a console to the virtual router and get in directly. Of course, you have SSH and console proxy for the access. All right, so this one I think is something Dag and Giles put together a blog. So there's a reference to that blog, and you must have seen this table earlier from the keynote as well. The other thing we did was, and this again to credit V, Zhao, Remy, and maybe a few other people who come up with the initial pull request. What they came up with was this idea. So the initial idea was, how do we reduce the downtime of a virtual router? Every time there was a new version of CloudStack, likely there was a new version of system vm template. And I have come across a lot of users who really like to upgrade. That of course is a joke. People don't like to upgrade much, especially when they they want to restart the networks. People don't enjoy that, and that affects their SLAs and etc. So the general idea came up with redundant VRs. So the idea for redundant VR is, you have a backup and a master. One of them can go down, the other one becomes the master, and your network stays on. The downtime observed could be 0 to the amount of time it takes the VRRP protocol to kick in, which I think is in the range of 1 to 3 seconds. You can tune that. So what Visa came up with was, so the earlier version that you would restart a network was, you will get rid of all the old VRs. So see, you have a bunch of old VRs, you got rid of them, but you have also upgraded CloudStack. There is no guarantee that the new VR may provision. There could be a resource issue, there could be compute storage, those kind of issues. So basically, there's a very functioning system, a virtual router and a guest VMs, those are running. You got rid of the old VRs, right? There's no way to back up, right? So you got rid of the old VRs, and there's some problem with the new VRs that come up, you're practically screwed. So the idea was, so in case of redundant VRs, the idea was, don't remove both the virtual routers. Don't remove your backup and your master VR. Instead, remove the old backup first, then provision a new VR. Once the new VR comes up, that new VR will become a backup virtual router. Then you destroy your old VR. When you destroy your old master VR, the new backup VR will become master, and then you provision the rest. And this way, right now with 4.11.1, sorry, with 4.11.1, if you're using a redundant VR in a network, we kind of observe almost 0 downtime already with this approach. And we kind of applied the same approach with non-redundant VR. So this table is network downtime observed for an isolated non-redundant VR. And we see a lot of improvements. Let me try to explain, at least in case of one hypervisor where we saw the most gain. In case of KVM and maybe Zen server, the reason the virtual routers start very quickly is because you have a base template, and the new virtual router kind of starts from that base template. So if you have the guest OS image already on a primary storage pool, and when you start a new VR, it just comes up. In case of VMware, what happens is that it will copy that disk. So whatever OVA file or a system template image you have, it will first make a copy of that thing. And disk I/O are probably the root cause of why it takes a lot of time. So in our test environment, for example, with 493, it takes 2 minutes for VMware for the VR to start up, because it's split in 3 ways. First, a copy of the disk is made. Next, the VR is started and patched, and third, it will be programmed. In our case with 4.11.1, with this near zero downtime upgrade patch, what we are doing is we first provision the new router. That means you basically copy the disk and start the VM, also patch the VM and start it, right? Then you destroy the old router, and then you basically do sort of a manual handover. And we see a lot of reduction in downtime. So for example, from 2 minutes if you're going from minutes to seconds, that's sort of what we achieved with this approach. And there is some future work where I think we want to maybe improve that further on. All right, so that was a comparison between the past and the present. Now, in order to basically go to the future, we have to understand the present. So I'll segue my talk into the current VR implementation. So the first question is, we have to look at, in order to understand the present, we have to understand how system VMs are born in the first place, understand the whole life cycle. So currently what happens is, any system VM, whether it is a virtual router, or a console proxy VM, or SSVM, first of all, the system VM template is copied on a hypervisor, on a primary storage pool, for example, and this VM will start. And based on a specific hypervisor, the command line, some initial options are passed to it. And the payload, the scripts, they are passed to this VM by attaching an ISO file which contains these 3 files. We'll look at that later on as well. And we also pass what kind of virtual machine is this? Is it a console proxy? Is it a shared network virtual router? Is it a VPC virtual router, etc.? And it kind of reboots on patching. Again, the new VR doesn't do that often, only in case of VMware in a very specific case. So here's the life cycle. I'm not going to go very deep, but just a blueprint of what it does. So we have a system VM template. We should know how to build it, how to patch it, how to upgrade that. So we have covered those topics. Then CloudStack comes into picture. CloudStack has its own understanding of networking, how a specific network type or topology is implemented. Then CloudStack will program the VR, and there are a bunch of features you can see the VR supports. So those are the different features, as you can see, supported by different binaries. So just for example, the DNS mask service, which runs in the virtual router, is responsible for DHCP and DNS. And you don't actually have to look at that, but maybe if somebody wants to reference that in future, I thought I'll just do a survey for everyone. So these are different features in CloudStack and different like tools and technologies we use to implement them. And I'll probably do some demo, and for the demo purpose, I'm using a KVM-based monkeypox. So this is a link where you can go and, so it's like DevCloud, but for KVM, we have to come up with a fancy name. So I think we came up with monkeypox. The first thing is, how do you build system VM template? So it's quite easy. You clone the repository, and there is a build script you run. If you're already on Linux and have KMU installed, that's it. You don't have to do anything. I'll skip this, but this is just for reference. Throughout my talk, I'll be skipping some of the slides because we, I think, have to complete this in 15 minutes. But if anyone wants to hack with me further, we have a session on Wednesday. So the first thing is, how does the system VM template itself patch? I think it does in 3 stages. The first stage is, there is a Cloud Early config script which is now tied to a systemd service. So this guy starts in the beginning. And so Cloud Early config starts, and the CloudStack will attach the systemvm.iso file. And there are different ways how it passes the command line options. So in case of KVM, it does by serial port. In case of Zen Server, there are 2 options. Zen Server uses pygrub to boot system VM template, so it can either pass the command line directly and inside the guest VM it will be available at proc command line, or you can use XenServer tool, or for example similar ways used by VMware by using OpenVM tool to basically read the initial options. In stage 2, this is present VR, right? So what we have done is we have created a bash script for each type of the virtual machine, and we'll basically look at that briefly. So that script is executed and it will magically convert your guest VM into that type of system VM. And then finally there is a post-init service which will conclude patching, start SSH and whatnot. And if you see on the right hand side, this is the flame graph that I was talking about. So using systemd, you can actually print out this thing, and the largest red part, so this is the cloud early config script, and this small one is I think is the post init script, and the last small thing you see here is the SSH server itself. A slightly bigger image for you to see, and these are the commands we use how to basically measure, and optimize your system VM template. So you can run systemd analyze, and it tells you the amount of time it has taken for us to basically start the virtual machine and patch it as a virtual router. On my laptop, it takes 11 seconds to start a virtual router, so I think not bad. And you can use systemd analyze plot to basically plot a frame graph. What I've done is, for the test environment, I have a local box running. So I have a local virtual machine. So this is a KVM box that I'm running, right? And this is my local management server I'm running. So I'm running a local management server here, and I have the virtual router deployed. And I took the liberty to basically plot that flame graph beforehand. So this is the flame graph for that virtual machine. As you can see, for the first almost 2 seconds, nothing happened. So this was probably the time it took the kernel to initialize itself and whatnot. And maybe from 2 seconds to 11 seconds, it did a lot of these operations. And this way of, these kind of tools that systemd has provided helps us to basically understand how to sequence the virtual router, how to optimize it, and see where the problems is. So for example, cloud early config took only 2 seconds, but cloud post-init service took 4 seconds. So maybe there is a mismatch or there's something wrong there. So we can use these tools and this approach to basically debug and see what's going where. Okay, getting back to the presentation. So basically this allows us to debug, and using this approach we could trim down the amount it takes to start a VR. The present VR, I think best case, for example, in case of KVM and on my laptop, can take 11 seconds. Maybe in production it can take lower or higher than that, depending on what kind of storage you have, what kind of server you got, etc. Okay, what is the ISO file? So the ISO file is used as a payload. So it is a way to push the payload in the system VM template itself. It has 3 main files. The first file it has is the authorized key file. So this is the SSH public key. In case of VMware, for example, this is used to patch the system VM. The SSH public key is how something can get in and out of the virtual router. The virtual router by default uses SSH and public key based authentication. There's an agent.zip file. This is only used if you are creating a CPVM and SSVM. And lastly, we have cloud scripts. It's a tarball, right? gzip tarball, and it has various scripts that are used to configure the virtual router. And then there are some details like how this systemvm.iso file is attached. So in case of KVM, this file sits on a KVM host, and the SSH authorized key is not used by KVM at all. Like we use a serial script, patch via socket script, to basically send the SSH public key. In case of VMware and XenServer, it gets it from the ISO itself, right? Not going to bore you with a lot of details. The only important thing from this bit is, in order to make any Linux box a router, what you have to do is you have to make sure that it is able to forward the packets. So that's the only thing I have to show you here. The other thing is just for reference if you want to dig deep. The last thing I would also say is sometimes the kernel can panic. For example, it is out of memory, the disk is full on the virtual router. So in that case, we have added some crash handling here at the very end, you can see. So if it panics, we want to reboot as quickly as possible. So there's a chance that next time it boots, it will maybe recover itself. post-patching. So what happens after the virtual router has patched itself using the command line options in the ISO file? It starts in SSH server, which runs by default on port 3922. And there are various ways to access your virtual router. So in case of KVM, there's a link local IP. Zen server also uses something similar. In case of VMware, they don't have a concept of a link local IP. We use the private IP. In your management server logs, you will see something like check SSH command. So this is something the management server tries again and again, periodically. Either the management server or the agent, that means the KVM agent, will do this. And basically, it will check whether it is able to SSH into the VR. Once it is able to SSH, you basically in your UI or through API, you'll see that the VR is in running state. I'm just going to, so these are just for reference. It's an old blog that talks about how do you debug and troubleshoot and whatnot. The only difference now is in case of KVM, for example. Let me show you a small demo here. So I'm going to go inside the virtual box, inside the monkey box. Let me see if it works. Did I mess up the networking? Okay. Let me directly use the console itself. So now, once you have SSH, let's say if you've got access to the Linux box itself, you can do virsh console, and you can say rs6vm. So you don't need to SSH. You can directly get into that virtual router. Let me do it once again. Let me exit, and if I try again, looks like something got messed up. So okay, so we are in. So as soon as I did virsh console, I'm presented with the serial console, and I can basically log in as root and password. So these are the default credentials. There's a global setting using which you can change the default credentials. And once you are inside the virtual router, by this approach, you don't actually have to use SSH. So it is handy in case you want to debug something very quickly. And the same goes for Zen server. So there is you can use XC tool, so you can use XC console and get into the VM that way. So that's just one additional way now to troubleshoot, etc. Okay, so these are the different network models that are supported or known and understood by CloudStack. So we got some sort of shared or flat network. So here the idea is you're switching the traffic. That means CloudStack VR doesn't participate in routing at all. Maybe the router gives you DNS and DHCP and all that stuff. For example, in case of shared network. In case of L2 networks, we don't provision a VR. We don't need that. I just thought I'll put in there. The other kind of network we support is a NATed network. That means the VR acts as a router, and it is routing between two networks. Example is the isolated network or multi-tier or VPC networks. The last kind of network, we don't officially support them yet, though we have a POC. So we have a special system interpreter that works in a different branch in CloudStack where OSPF plus Quagga exists, and we can route. So CloudStack router can actually route and talk to the core router, get the network routes, etc. I'm just going to skip this. I'm pretty sure everyone knows their layers, but the general idea is that your kernel, it doesn't matter what kind of operating system it is, but when someone is talking to, like a client is server a client is talking to a server and whatnot, so these are the different layers it gets into, and at least the developer should have an idea between what layer 2 to layer 4 means, because that helps a lot in debugging and like writing a new feature for virtual router, etc. And again, a lot of people would also like to play with physical networks, this is a small lab I have had in my university days. I thought I'll just put in there. All right, so isolation mode. This is a very good concept. Like, so my boss asked me to, put in some. So I asked him, can I put in some cat gifs? And he said, why not dogs? So this is for Giles. All right, so isolation mode. So these are the VLAN. I think is the default isolation method we have in CloudStack. Like by default, you can use a virtual router, have some VLANs, and start. In case of KVM, we also support VXLAN, and then there are different providers and different ways of doing isolation of networking. If I have time, I'll do some sort of demos around this, but I'll basically write that in order to, let's say, work on a future version of virtual router, it needs to support these kind of isolation methods. So that's the basically point. And the general idea is that VLAN is just a header in the network packet to basically tag and untag. Similarly, in case of VXLAN, we are encapsulating. And in case of, for example, Linux kernel, the encapsulation and decapsulation occurs in the kernel, so it's very fast. So if you want more than, let's say, 4095 networks, then go with VXLAN. And of course, if you have KVM. A lot of people also have trouble understanding what exactly is VLAN. So if you have time, we'll actually look at VLANs. And that's probably going to be a fun exercise if we get time. But the general idea is a router is responsible for switching a packet across networks. If, let's say, there are two guest VMs on the same network, router is not in the picture in their communication at all. Like if two virtual machines, guest VMs are on the same, let's say, isolated network, the virtual router comes into picture only when they want to talk to the outside or the outside wants to talk inside. If the guest VM wants to talk to each other, right, they get switched by the bridges itself. So virtual router, the traffic doesn't actually get to virtual router. So some basic core concepts you need to understand. Okay, it's time for some pretty pictures. So these are examples based on KVM. You can experiment. On the left-hand side, when let's say you create a bridge, a network in CloudStack that is untagged. So you can actually create a custom isolated network in CloudStack which is untagged. So create a specific network offering, create a network that accepts custom VLAN ID, and the VLAN ID you can put VLAN as untagged. So you basically end up fooling and creating a system like this, where you have physical NICs on the host that basically end up connecting to a bridge. And that bridge can basically, these are the VNICs. So these are tap interfaces. You got TUN and taps, right? So tap is the interface. We basically L2 interface, like a virtual software interface that gets plugged into your your guest VMs, and that's no isolation. On the right hand side, what happens is you have an actual physical Ethernet device, and then you basically create a VLAN device. Basically, let's say you have H0 and you want VLAN ID 2, so it will be H0.2. It will be plugged to a bridge, an L2 bridge itself. In case of KVM, so we are talking about KVM. So this is an L2 bridge, and it will basically connect itself to VNIC. It could be so the VNIC could be plugged into a guest VM or the virtual router itself. Now, what you actually want to understand is, the whole point of this slide is that until this point, there is no concept of isolation. The VLAN tagging and untagging is by this device. So the virtual router, the point I'm trying to make here is, virtual router itself doesn't know about isolation. The virtual router does not actually do VLAN tagging or VXLAN tagging or what have you. It is on the host level or the hypervisor level where you basically have some sort of network device which is handling this. And this will come handy when we debug debug networks. The other reason I put in those slides were a lot of new people want to come and join the effort towards the future of virtual router, and it's important to understand the present, so we can do something about the future. These are some simple examples how you can experiment in KVM. So Worst List can do the listing. You can do IPA to say get the number of all the interfaces. You can do BRCTL show, and there's BRCTL I think show MAC addresses, and using that you can see the ARP table of that specific bridge. So you can actually understand how networking works and whatnot. And these are some handy tools to look at the IP table rules and EV table rules. We'll experiment that at the very end if we have time. All right, so these are the network types that we ought to support. The future virtual routers need to support these various network types. So we got L2 network. Nicholas is sitting there. So he was the guy who implemented L2 network. Isolated network, so we got isolated single tier basically network and VPC. What you actually see here is, if I as a developer were to look at this at the with fresh eyes, I'll say isolated network is a special case of VPC network with just one tier. So that's just one idea. You can refactor the isolated network and VPC network into a kind of network that supports multiple tiers. So that's like one way to think about what future we can aspire for. The next thing is a shared network. So shared network is available, I think, in both basic zone and for advanced zone. I think in case of KVM, you can also do security groups in advanced zone. So another idea, we don't need a different zone type. We don't need basic zone and advanced zones. We can just refactor it as a zone. And if you want shared network, you can just create a shared network, whether irrespective of what kind of zone it is. So we've got hard-coded technical debt that we have accumulated, and those are the things we can work in the future of VR to basically solve and fix. Okay, let's take a deep breath. VR programming, it's probably the most ridiculous thing I've come across, and there's no single, I have to refactor and learn a lot in order to create the present VR, like migrate to the present VR. So in CloudStack, there are two interfaces, or you can say classes, called virtual routing resource and virtual order deployer. These two guys are responsible for doing mainly 2 or 3 things. One is to create like a file or something in the virtual OODA, and other one is to execute that. And for every hypervisor type, you can extend that feature and basically implement the mechanism, like how do you get into a VR and create that file, or how do you get into that VR and execute that thing. The other thing I learned was the executable scripts are in this location of Cloud bin. So whatever you are executing, whether you are trying to add a new VM, adding new DNS and DHCP entries, whether you want to like attach a VPN, like start a VPN service, or do whatever. So all those scripts are in that location. And I also found in case of KVM, there's something called as router proxy. So the way it works is the management server talks to the host, calls this file, and this file internally SSHs to the virtual OODA at the link local IP on the port 3922, and then executes stuff in the VR. So we have got a lot of things going on here. The next thing I see is the payload from the management server is deployed in the virtual OODA as a JSON file. That JSON file is read by some Python script, and then it is processed and gzipped and moved to this specific folder called for cache cloud process. And if that was not ridiculous enough, there's another file. There's another way of pushing the payload. So there's something called as a config file. It is an XML with JSON and a lot of payload and whatnot. And it creates this vr-uid.cfg file. And so when you do a restart, it does aggregation and applies several rules and several types and whatnot in an XML file that has JSON in it. And it is executed by a different thing, right? And the last thing is there are a lot of, CloudStack VR tries to do a very bad job at diffing and applying the changes. And whatnot. So what I see from all of your faces is, you're like in the panic mode. You're like, what's happening? There's so many details, right? It has to be very simple. It has to be a very simple process. Like CloudStack decides what the VR should do. It gives that information to the VR, and the VR should apply. That's all. It should be very easy for a new person to understand and basically make changes in the VR code. So I think that's what we want. Right? So we want some firepower from new developers, right, who basically help us refactor this part of the code base. The entire VR code base is 2,000 to 3,000 lines of Python code. I believe we can do that. We can refactor and maybe improve. We can even get some sort of agent, or we can explore different technologies or different ways. How do we program the VR consistently? How do we patch? Can we do online patching? That means a VR is already there. We don't need to destroy the old VR, create a new one, and patch. So those are the things I think we want to explore, and not be like this cat who's in the panic mode, right? Okay, let me also survey with some pretty diagrams. So these are all examples from Monkeybox. You can download and play on your own laptop. These are just diagrams of the network setup. So in order to move to the future of the VR, we also need to understand case by case basis how different NICs are configured, they're plugged in and whatnot, and can we unify that? And I'll explain like what I mean by unifying. So take this example. This is an example for a SSVM or a CPVM virtual machine. What happens is the SSVM or CPVM virtual machine has at least 3 NICs on it. So H0 is used as a link local. So that means link local is only used for programming purposes. The management server or the management server via the router proxy script goes to the box, to the host, and then goes to the loopback or the link local IP on port 3992, so it SSHs and whatnot. The Eth1 and Eth2 are connected to a bridge, so your private network. So in some cases, you can have a different network bridge. As part of KVM host setup, you have to create these bridges. So this is an example of a bridge-based host KVM setup. You can have OVS or you can have something else. Let me wrap this up. So the point I'm trying to make is, for one kind of hypervisor, the way we access the virtual router is different. For another kind of hypervisor, it is different. So we probably want to unify that, make it very simple, and see how we can do other things like do online patching and things like that, right? Here's another example. So this is an example of an L2 network. You see guest VMs have single NIC and they're connected to a bridge, which most likely is a L2 bridge, which in turn are connected to some network or bunch of NICs that you have configured. This is L2 network with VLAN. So see the difference. The difference between this slide, I'll give you a moment to look at that, right? Look at the Cloud 0 device. So in the previous slide also, right, Cloud 0 and Cloud 0. So in this case, the Cloud 0 bridge exists on the host, but it is not connected to any physical Ethernet device. Why? Security reasons. You want to get into the host, program the VR, and get out. That's the only purpose. In case of L2 network, there is no VR, so that's why you actually don't see a VR there. There's just guest VM that is connected to a bridge directly. In case of L2 network with a VLAN, that means you are using VLAN-based isolation, there'll be a bridge that the KVM agent will create, right? This bridge, again, doesn't know anything about isolation. It doesn't care about VLAN. This bridge itself will connect to an Ethernet device that is VLAN enabled. Again, connecting to your actual physical NIC. So that's how it kind of works. Similarly, isolated network with VLAN, right? So virtual router with 3 NICs, one connecting to the link global for programming purposes. There is a guest network on H0. So bear in mind, in case of isolated network, the guest network is implemented by H0. And why I'm stressing on this point will come to know in a sec. And H2 is for public network. So all your SNAT IPs, public IPs that you attach, they will be on the H2 interface. There is a guest VM that connects on this specific bridge, which is VLAN enabled by this device, right? And that's how it works. When we go from isolated network to VPC network, see the differences. Link local IP is H0. In case of isolated network, link local IP is H1. So again, as a developer, when I'm debugging a network, I have to remember those things. Someone will come back and say that one guest VM is trying to use the public IP to access another one. It is not working. So this is the classic hairpin nut problem that we have come across. We got all those things fixed, but as a developer, I need to know and keep these diagrams handy, or at least in my mind somewhere to know what I'm working on. VPC, again, if you see the public network, so public network in case of VPC virtual router is on H1. In case of isolated network, the public was on H2. So again, there's a mismatch with the numbering and ordering. We want to fix that for future virtual router. And one of the aims that I think I want to propose here is we want to club the isolated network model and the VPC model, because to me, the isolated network is a VPC network with just one tier. So probably if we make everything uniform, then it will be easier. Lastly, in case of VPC virtual routers, all the guest tiers that you keep adding, they start from H2. So H0 is for link global, H1 is for the public, NAT IP. And as you keep adding your tiers, we keep adding the NICs, and they basically get, it's the same story all again, right? So there is a guest tier that connects to a bridge. This bridge itself doesn't know anything about isolation, but it connects to a device that knows, right? And things like that. So same with VPC. Again, these slides will be for your reference if you want to dig deep on them. Shared network, no isolation. So again, the virtual router has a public and link local. The public thing connects to a bridge, and this is what happens. This is a more practical use case where you have shared network with a VLAN. So again, a virtual router. The virtual router in case of shared network only provides DHCP and DNS. So that's why you don't see a guest interface or something like that, right? So again, there's an interface, there's a bridge that connects to the VM, and that bridge also connects to a VLAN aware Ethernet device, which is which does the the VLAN tagging and untagging. All right, security groups, very special use case in CloudStack. So security groups, basically the isolation happens at the host level itself, and it happens on the bridge itself. So the isolation, right? So there's a file called securitygroups.py, and uses both IP tables and EB tables. So basically these are networking firewall rules on the bridge itself. So rules are applied here, and as you can see here, there is no VLAN tagging here. I think you can if you want, but there is no need. Security groups, I think, in my opinion, the most new or cloud era network topology, massively scalable and whatnot. All right, so I think I'm approaching, I just have 5 more minutes. So in order to go to future, like think about a future of virtual-root, we also need to learn from others. So what I did was, this year I did a comparison between OpenStack and CloudStack. Here's a link, you can go and see. One thing that that was like I really loved about OpenStack was they had a network designer where you can drag and drop seeders and routers and put this and that, more graphical, and I really liked that. I think probably that's something I would want in CloudStack. A very flexible tool to create networks. Give that plan to CloudStack, and it basically creates this network for us. We can also learn from Kubernetes and CNIs, other projects like Flannel, Calico, Weaveworks, etc., how they are solving a networking problem for their communities. And while that might not be directly related to at the IS level, but that gives us idea of how they are using. For example, even though Kubernetes is a newer technology, it is still using IP tables for a lot of pod services and all that implementation. So it gives me assurance that I don't need to look at the cool things and leave what I have now, which is rock solid and working. I can still build the future of VR on known battle tested technologies like IP tables, NF filter framework, etc. And of course, I can look at other open source virtual routers. So a virtual router, what at the core is doing is it is getting some sort of payload, it is processing that and providing a functionality. VYOS is an example. So Vyata kind of open source their virtual router, and I think there's a pull request where somebody was trying to integrate that with CloudStack. So maybe virtual router is something that we may not need to write from scratch. We can just have an implementation or support from others. Here's what I've learned. I've learned the build and patching process of the system VM. Right, I've learned various network models and topologies and whatnot. I've learned one major thing, which was I've seen VLANs. That's what I'm trying to say. I've seen that virtual router itself is unaware of the isolation, right? So using TCP dump and whatnot, I was very happy to see VLAN tagged packets and basically understand end to end how everything kind of worked together. And also, I learned that a lot of the stuff that runs in the virtual router are services like the web server, VPN, etc. They could be containerized. And here I have some ideas for the future. So we can again improve the virtual system and template upgrade process, build process, patching process. We can make sure the next future version of virtual routers are redundant capable. The reason why we have very small downtime in case of redundant virtual routers, they use something called as keep alive D, which does VRRB, and it uses battle tested contract D, which is a daemon or a process or a subsystem in the Linux kernel itself that tracks live connections, does a state transfer using UDP and passes. So we can use this clean state transfer handover technology in the future version of CloudStack. So even if you have a network which doesn't have a virtual router that is redundant, if you make it redundant capable, an older version can migrate to a newer version easily. And again, the next thing is refactor the VR code, make it speed up. We have to migrate from Python 2.x maybe to that. There is a new subsystem or tooling, so we have to move to NF tables, IP route 2. And here's a bold idea. Why not even get rid of virtual router? Maybe explore other technologies, work with online patching of things. And those are some things we have to research and develop. Getting rid of virtual router is a good idea. Like all the stuff in the diagrams, for example, we saw here, right? these could be, so all the routing was happening on, let's say, let's take an example of isolated network. So all the rules on H0 and H2, those could be NICs on the host itself. Those could be a process, container process on the host itself. So there is actually no need of virtual router. And I know few people in the community have written to me privately that they are probably exploring that as well. In some network implementations, for example, if you don't need the web server, you don't need VPNs, maybe there's a way to explore that. People are already working with config drive and whatnot. So it's time, so I'd like to thank everyone for their time, and we are hiring. Any questions, guys? Okay, thank you very much.